All right, let's solve another problem here. So here we have oxygen that enters an insulated 12 centimeter diameter pipe with a velocity of 70 meters per second. We know that at the inlet, so let me draw this out. At the inlet of the pipe, we know that the pressure is 240 kilopascals. The temperature is 20 degrees Celsius. And at the exit of the pipe, so we'd have flow going this way, we have the pressure at 200 kilopascals and the temperature at 18 Celsius. We are asked to find the rate at which entropy is generated in this pipe. If we look at the fluid that we're dealing with oxygen. And if you browse through the tables that you're provided with in the textbook, you will see that, fortunately, we don't have the thermodynamic tables for oxygen. However, we do have some relationships that will help us to approximate the change in entropy of oxygen in this system. And remember, this is a insulated pipe. So we don't have entropy generation to the entropy transfer to the surroundings. If you guys remember too, we have entropy generated equals delta S system plus delta S surroundings. Delta S system, I think I would feel safe to say, would be our inner diameter of our pipe. Looking at the amount of delta S to our surroundings, knowing that there's no heat transfer to our surroundings, there's no mass entering the surroundings through the sides of this pipe, we can say that the entropy generated through the sides of this are negligible. So let's calculate now our entropy generated in this pipe. So here we have our delta S system, which is our mass flow rate times S2 minus S1. We can approximate this S2 minus S1 using some relationships we talked about in class. So let me log on to our class system here, and let's talk about those. So here we have the entropy change of ideal gases. So this oxygen would be categorized as an ideal gas, and we have some approximations for these. So here we have determining first if it's an open or a closed system. And we have an open system, so we'll use this second equation here that's provided. So here I will have Cp average for the oxygen times ln of T2 over T1 minus R of oxygen times ln of P2 over P1. So a couple properties we need to determine here. We have the temperature and pressure at the inlet and exit, but we don't know the Cp average. So to determine Cp average, we calculate temperature average, which is T1 plus T2 divided by 2. So we see the temperature drop some as it passes through this pipe. And so here our average temperature is 20, it's 18 divided by 2. Plus 273 is 292 K. Our R for oxygen we will also determine from our tables. So let's flip over to the tables in the back of our text. and we'll look at some of the ideal gases that we're dealing with here. So here we're dealing with oxygen. So here you see oxygen in the lower right hand corner of this plot. I'm going to take, for simplicity, just the properties so I don't have to interpolate. The properties of oxygen here at 300K. So at 300K, the CP average, I will say, is 0.918. We can also grab the ideal gas constant for oxygen off of this table here. So we have that available to us as well. So it's 0.2598 kilojoules per kilogram K. Okay. So let's plug these into our equation. We have mass flow rate times CP average, 0.918. And let me just expand this here. 0.918 kilojoules per kilogram K times ln of T2. So 18 plus 273 divided by T1. So we're converting these to absolute units. So please be mindful of that as we want to make sure that if you have an ln of 0, if you try to plug that into your calculator sure won't like that. So to avoid that, we make sure to use our absolute units here in this calculation. So R, here we have 0.2598 times ln of P2 over P1, pressure 2 dropping as it rolls down the pipe. So let me do a few calculations here. Let me calculate this first one. So here we have 0.98. ln. So this is negative 0.0063 kilojoules per kilogram K. And here we have plus 0.0474 kilojoules per kilogram K. So adding these two together, we will have 0.0411 kilojoules per kilogram K. So I guess technically we could leave it at that, leave it like this, but I guess for completeness, we'll make sure to multiply it by the mass flow rate. So let's calculate the mass flow rate for this stream. Note the mass flow rate of our fluids. Mass flow rate of our fluid is density times cross-sectional area times the average velocity. So our density of oxygen, we don't know right now. The area, we're given the diameter of the pipe, so we can calculate that. So here we have density, area, pi over 4 times 12 centimeters, 0.12 meters squared. And the velocity at the inlet of the pipe is 70 meters per second. So really all we need to determine here is the density. We can get the density from the ideal gas law. the ideal gas law in its classical form being PV equals MRT. But we can see that we know that density has units of kilograms per meter cubed. So if we divide both sides of this equation by volume, we can see we can rewrite this same equation as density P equals density times RT. So let's solve for density. So the pressure at the inlet, or state 1, 240 kilopascals. So this is a Newton per meter squared. Divided by the R of our fluid, 259.8 joules per kilogram K, times temperature at state 1, which is given at 298 K. So density, let's take a look at our units also. I'm going to rewrite joules here as a Newton meter. Joule is a Newton times meter. And then we can see that Newtons cancel. And our units, we are left with kilogram per meter cubed. So let me run a quick calculation here. So I calculated this to be 3.1 kilograms per meter cubed. So with that information, I can calculate the mass flow rate. Mass flow rate is 3.1 times pi over 4 times 0.12 squared times 70. I calculate the mass flow rate to be 2.454 kilograms per second. If we go ahead and finish this problem, we have this as 0.1 kilowatts per K as our change of entropy in our system, which we have determined to be the same as the change of entropy, as the amount of entropy that is generated for this system as well. So hopefully that problem was helpful, dealing with the ideal gas and looking at it, the entropy generated for a system and how we approach that for an ideal gas.